Hey guys, in this video I'm going to explain about the Carnot cycle. Okay, so first some brief introduction. So the Carnot cycle was created by the scientist Nicolas Carnot. He proposed the best known reversible cycle. Okay, so Carnot cycle is talking about a reversible cycle. In the previous topic, you have learned about reversible processes and irreversibilities. Okay, so in real life, processes are not reversible. Okay, but the reason that we are studying the reversible cycle, or specifically the Carnot cycle, is because we want to know what is the highest possible efficiency that an engine can achieve when operating between two temperature reservoirs. Okay, two different reservoirs, and this is the engine, right? So we want to know the highest possible efficiency, so we must have the best possible process, and the best process is where there are no irreversibilities. Okay, that means no friction, no unrestricted expansion, etc. So if you want a list of irreversibilities, you can go to chapter 6 part 2, right? So the Carnot cycle is just a cycle, and it's assumed that this cycle is implemented on an engine to produce a Carnot heat engine. Okay, so we're always comparing the Carnot heat engine with normal heat engine. Okay, and the efficiency of the Carnot heat engine is always bigger than the efficiency of a normal heat engine. Alright, so the Carnot cycle is composed of 4 reversible processes. So for it to be the best, all 4 of the processes have to be reversible. Alright, so they are 2 isothermal processes. Isothermal meaning constant temperature. 2 adiabatic processes meaning heat transfer equals 0. So this person, this Nicolas Carnot, came up with these processes. So these processes are able to produce work just like the heat engine process, where you have the heat addition in the boiler, and then the turbine does work, etc. Okay, we have that too, and the working fluid here is an ideal gas. Alright, so let's look at the 4 processes now. Okay, this is what we aim to produce. We're going to see the process on a PV diagram against all 4 stages of the process. Okay, so I will sketch this as we go with the explanation. Alright, so there are 4 stages. So the first one is isothermal expansion. Okay, isothermal expansion means that the gas is expanding isothermally. So T equals to constant. So how do you expand a gas and keep its temperature constant? Okay, so that means the temperature, the gas has to be in contact with a source that has a constant temperature. So you have learned about reservoir. You know that reservoirs are able to maintain their temperature regardless of the heat that they give out or absorb. Okay, they are able to maintain at TH. So this piston is originally insulated, but we remove the insulated part at the top here. Okay, we remove it and then we put it in contact with an energy source. So what's going to happen is heat will be transferred into the system, which is the compartment of the cylinder, and the piston will move. Okay, so what's happening here, we can look at it on the PV diagram. Okay, so initially it's at some pressure and some volume. Let's say it's here at point 1. So it's expanding isothermally. If you recall, boundary work, isothermal expansion, isothermal compression, we also did a graph there, and to find the boundary work is a P1 V1 ln V2 over V1, all of that. Okay, so my point is the isothermal expansion or compression looks like this. Okay, something like that. Let me okay, something like that. It's expanding isothermally to another volume. So we can see that the volume has increased. So volume has increased from point 1 to point 2. Okay, pressure has reduced a little bit as a result of the process being isothermal. Okay, next, the insulation is put back. So there's no more heat transfer. So the second process is called adiabatic expansion. So the gas is allowed to expand. Okay, the expansion continues, except that now insulation is placed, so there are no more heat transfer. So as a result, something has to be sacrificed, right? Because it's expanding, but there's no energy input. Therefore, the temperature will reduce. Okay, so while it's expanding from point 2 to point 3, the temperature will reduce. Okay, so what's happening here is it's expanding, and because of the temperature reduction, the pressure also is reduced. So this is something like that. Okay, it's not a straight line, right? It's slightly curved. So from this isothermal line, it sort of jumps to another temperature. Alright, so that's adiabatic expansion, no heat transfer. Right, or heat transfer equals to 0. Next, it has reached point 3. So at point 3, the insulation is removed again at the top, and the cylinder is put in contact with a reservoir or a sink. Sink is at low temperature. Okay, so number 3, it's isothermal compression. Okay, so when put in contact with a sink, this is to ensure that it remains at a constant temperature. So this is an isothermal process again. Alright, so what's going to happen is whatever heat that is inside will be transferred to the sink. Okay, heat will be leaving. It's the exact opposite of the first process here. Okay, here heat is added, here heat is removed. And what happens when heat is removed isothermally? The system will be compressed. Okay, so this is one isotherm line. So we have another one. Okay, so it will go this way to point 3. I'm sorry. Oops, I got the numbers all mixed up. This is 3 and this is 4. Okay, so isothermal compression, T remains constant. Okay, also you can calculate the work done here using the equation that we have learned in chapter 4, boundary work. Okay, boundary work equals to P1 V1 ln V2 over V1. And finally, at point 4, an insulation is placed again at the cylinder. It's just the opposite of the second process. Alright, so the gas is compressed continuously. So what's going to happen is the heat can't escape anymore. Okay, it's still compressing the gas, heat cannot escape, therefore it will build up and the temperature will increase. Okay, so process number 4 is adiabatic compression, and that is the opposite of the second process. Right, so we have that. Now if you look at the direction of the processes on the graph, 1 to 2 is an expansion, 2 to 3 is an expansion, and 3 to 4 is a compression, and 4 to 1 is a compression. So you will have two parts. Let's see. Okay, so this is where work is being done by the gas. Okay, the piston is expanding, which means work is done by the gas. Okay, it's all area under the curve, if you remember from chapter 4. Okay, area under the curve. So all the yellow portion is work done by the gas. Okay, and let's see, maybe another color. Okay, so for processes 3 to 4 and 4 to 1 is in the opposite direction, right? It's becoming smaller. This volume becoming this volume, and this volume becoming 1. So this part is the work done on the gas, the compression work. Okay, the yellow is the work done by the gas, and the blue lines are the work done on the gas. So if you put them together, you get a net work of whatever you see inside this enclosed area. Okay, this area will be the work produced by the cycle. Okay, for more information, you can look through the slides. There are some details like all this. Okay, and you could also go to YouTube and look for Carnot cycle. Please bear in mind though that the explanations given are a lot more than what I explained to you here in this video or in the class before. Okay, so there are a lot of extra information. It's good for you, but I don't want you to get more confused. Okay, so you can go ahead and watch them, and you can ask me any questions if there are anything that you don't understand. Bye.